I've got another problem up here on the board. Same directions as last time, although I didn't bother to write them out again. We've got this function and this region. I want to first of all confirm that there is an absolute max and min. Then I want to find the location and value of them. Okay, so this function is continuous. Notice this region here, D, is just the solid unit disk. The boundary curve is x squared plus y squared equals 1. We're including that because it's an inclusive inequality. And we would be less than 1 on the inside of that disk. So that region is closed and bounded. So this is continuous. This region is closed and bounded. So the extreme value theorem ensures that there is an absolute max and an absolute min. So I'm going to create here my master table for points xy that are the possible locations, and then f of xy, which would be the possible values for the absolute max and min. And I know I need to check two types of points: critical points and points that are on the boundary. Okay, let's find our critical points first. So the gradient of f, that's always just partial of f with respect to x, comma partial with respect to y. In this case, the partial with respect to x is y, and the partial with respect to y is x. That gradient is always defined, so no critical points from an undefined gradient, and the gradient of f will equal the 0 vector if both of these components are 0. So y would have to equal 0, and x would have to equal 0. Well, that gives me the origin, and that is included in that disk. Again, remember when you're working on an artificially restricted domain, not the natural domain of the function, do always check that the critical points that you find are actually in that region. Okay, and of course 0 times 0 will give me 0. Okay, now the boundary, in this case there's just one boundary curve because it's just the circle. In the last example we had two separate sections for the boundary, and we had to make sure that we parametrized each one of them. Okay, here I can say that my boundary is just r of t. Unit circle, I'm just going to parameterize as cosine of t times sine of t, but I am going to restrict my domain because I want to get this just once. So I'll say from t is between 0 and 2 pi. Now I don't have to choose that particular interval, but I do want to restrict the domain for two reasons. One, I want the extreme value theorem to apply, which means I need to be working on a finite closed interval. That way I can use the extreme value theorem for functions of one variable, assuming the function that I get when I plug this into f is a continuous function of t. The other reason is I only want to have finitely many critical points. These functions are periodic. If I don't restrict my domain, I can expect that I'm going to get infinitely many critical points that would be different values of t corresponding to the same location on the circle. So I really want to parameterize it so that I just get the circle once. Remember, that's just the curve. That by itself has nothing to do with f, so I've got to plug into f. So f of r of t, that was x times y, that becomes cosine t times sine t. Now, here's a place where if you remember your double angle formulas, you might notice that that's half of sine 2t. Not absolutely necessary to notice that, but if you do, it might be a little bit faster when you're taking the derivative. Okay, so this is a continuous function. Either way I write it, it's continuous. We're working on a finite closed interval, so we can use the extreme value theorem for functions of one variable. Okay. So I'm going to create a table just for the boundary. I usually have a master table for my critical points for f overall, and then my points on the boundary. And I usually will just create a separate table for each portion of the boundary, simply because those are also going to have t values. But there's no t value for this critical point because that wasn't on the boundary curve that I parameterized. xy and then f of xy. And so I'm going to check critical points But notice these will be critical points of f of r of t, not critical points of f, but critical points of this function composition. And then we'll check our endpoints. Now the endpoints that I've given us are 0 and 2 pi. Those endpoints are actually quite arbitrary. I chose them because I wanted to make sure I was working on a finite closed interval, and I wanted to make sure that I was only getting each point on the circle once, so that each critical point I was only going to get once. Okay. But I could have just as easily parameterized this from pi to 3 pi, or from negative 5 pi to negative 3 pi. Any interval of length 2 pi will work. So what that means is that these endpoints aren't actually particularly important. The only way the endpoints are going to end up being locations of a max or min are if they also end up being critical points. Because I could have chosen a parametrization where I didn't get these points, so the only way they'd show up on the list is if they were critical points. Okay, you can explain that, or you can just check the endpoints. Okay, you can't just leave them off, because if you leave them off, I'm not going to know whether you forgot to check the endpoints or whether you realized that in this case, because the endpoints are arbitrary, because any interval of length 2 pi would do, that if the endpoints are the location of a max or min, they'll also be critical points. I won't know that you knew that unless you write it out. And I think it takes more time to write me a note. Dear Carla, I know I don't need to check endpoints in this case because the endpoints are kind of arbitrary and blah, 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 blah. I think that takes longer than just checking them. So I'm just going to check them. Okay. So 0 and 2 pi, they actually both correspond to the same point on the circle, 1, 0. Okay. That's because in order to include both endpoints, I actually had to come literally full circle so that my starting and ending point are the same. Okay. So x times y will just be 0 at that point. All right. So let's find our critical points. Now that means I need to take a derivative. Need to make sure that I'm working with this function of one variable. I'm not taking the derivative of my vector function. I've plugged it into f. So the derivative with respect to t of f of r of t. Now if I work with it this way, I'm going to be using product rule. So I would be getting the derivative of sine is negative sine t times sine t plus cosine t times the derivative of sine is cosine of t. I'd be getting cosine squared t minus sine squared t. If I work with this version, I'd be getting 1/2 of cosine of 2t times 2, and that 2 would cancel. This happens to be, cosine squared minus sine squared t, happens to be the double angle formula for cosine. Okay, so, excellent. I can work with either version of this derivative. Notice, it's always defined. Okay. So then it's just a question of where is it equal to 0. Okay. I'm actually going to go ahead and work with this version, cosine squared minus sine squared. Let's see. Yes. If I have cosine squared t minus sine squared t equals 0, that means cosine squared t equals sine squared t. That means the square root of cosine squared equals the square root of sine squared. Be very, very careful. That's the absolute value of cosine t equals the absolute value of sine t. So cosine of t is plus or minus sine of t. Okay. Now, students sometimes say, why don't you have a plus or minus on both sides? Well, I could, but if I say plus or minus cosine t is plus or minus sine t, that gives me exactly the same two options. Either cosine and sine are the same number, or they're the opposite number. Okay. So I only need to write the plus or minus once. Notice, because of the plus or minus, if I think of t as an angle, I'm going to be getting a point in each of the 4 quadrants. In quadrants 1 and 3, I'll have a solution to cosine is the same as sine. In quadrants 2 and 4, I'll have a solution to cosine is the opposite of sine. But for all of my solutions, the absolute value of sine and cosine has to be the same. So that tells me that my reference angle will have to be pi over 4. Okay. So my angle in quadrant 1, actually let's draw each one of those angles over here. So I'll have 4 solutions. In quadrant 1, I'm just getting pi over 4. In quadrant 2, there's my t. My reference angle is pi over 4. And so t would be pi minus pi over 4, or 3 pi over 4. Okay. In quadrant 3, there's my reference angle of pi over 4. T is pi plus pi over 4, so that would be 5 pi over 4. And then in quadrant 4, my reference angle is pi over 4. T is 2 pi minus pi over 4, so that would be 7 pi over 4. Okay. Those are going to be my 4 critical points, just because we did restrict the domain to be between 0 and 2 pi. If I hadn't restricted the domain, I'd keep going around the unit circle and I'd get infinitely many critical points. All right, I think I want to make my table just a little bit bigger so that I can list all of these values. So I'll give myself some more room for my 4 critical points. And then my endpoints we said were 0 and 2 pi, both of which corresponded to 1, 0, and gave us a z-value of 0. Okay, so if t is pi over 4, xy is root 2 over 2, root 2 over 2. Cosine of pi over 4, sine of pi over 4. If t is 3 pi over 4, my point xy will be negative root 2 over 2, root 2 over 2. Same absolute values, but if this is my point that was in quadrant 2, there my x value will be negative and my y will be positive. Okay. 5 pi over 4, they're both going to be negative, so negative root 2 over 2, negative root 2 over 2. And 7 pi over 4, now x will be positive, but y will be negative. Root 2 over 2, negative root 2 over 2. F of xy was just the product, x times y. So here that's going to be 2 over 4, or just 1/2. Here where they're opposite signs, I'll get negative 1/2. Where they're the same sign, I'll get positive 1/2. And where they're the opposite sign, I'll get negative 1/2. So if I look at the z values on my table, I can see I've got 3 different z values, although each one occurs twice. This doesn't really count as twice because it's the same point, but different t values. Okay, so there's 0, there's 1/2, which is positive, and negative 1/2, which is negative. Obviously, the positive one is going to be my max, and the negative one is going to be my min. So notice, there's only one max. It is 1/2. But the location of the max is not unique. It occurs at 2 points. Okay. All right, so I could add this information over to my master table. I think what I'm going to do, rather than recopying it, is just say see other table. But I want to make sure that I'm comparing these z values with this other z value from my master table. Okay, the 1/2 and the negative 1/2 are still the biggest and smallest values, even when I include this z value. But if at my critical point I'd had a z value of 1, that would be my max, and my min would occur on the boundary and be negative 1/2. Okay, so let's see. Let's just state the answer to our question. So the absolute max is 1/2. It occurs at 2 different points. Now I can write those out if I want to. What I can also do, and I'll sometimes do this, when I've got lots of points and they take a while to write, I've just sort of labeled my points A, B, C, and D. And so the maximum occurred at point A and C. the absolute min is negative 1/2, and it occurs at these 2 points, so at points B and D. That's totally fine. In general, I like to have a master table and then a table for each section of the boundary. Sometimes there are enough points that it's kind of tedious that it's okay to just say, hey, look at the other table, rather than actually copying everything onto one. And very often I will do this, labeling my points with just capital letters so that I don't have to rewrite the coordinates multiple times.